The next speaker is Leonel Romero, who joined my group, I think, in 2003. Is that correct, Leonel? And about a year later, we had a big experiment in the Gulf of Tonopec. We managed to get the in-car C-130 aircraft for about 5 weeks, and along with Jessica Kleiss, another student of mine, we spent that time in Huatulco, flying out of there out into the Gulf of Tonopec, measuring the wind and the waves and looking at the development of the wave fields. And Leonel's thesis was involved in actually modeling the evolution of the wave field, and I think it's probably the most recent example of being able to compare, in this case, a slightly modified WaveWatch 3 version of the wind wave modeling to actual data. I mean, you'll see a lot of wave modeling papers, but you won't see that many that are actually comparing the results to real data, and I think this was an important piece of work. Leonel went on to show that some data that Dave Drazen, who I think is at the back of the room, some data that Dave Drazen collected in the lab, and we had a simple ballistic model for the dissipation of braking for that lab data. Leonel was able to show that with the available data at the time, that a very simple adjustment to that ballistic model to include a threshold slope actually included all the available experimental data at that time, and the support for that, I think, has only continued in the intervening years as more lab data has become available. And subsequently, Leonel went on to show that how important the high-frequency tail of the spectrum was, and he was able to use the information that we'd gathered from the lab to predict, in part, what that high-frequency tail should be. And when we were subsequently able to test that, there was strong support for what he'd done. He subsequently, he continued on as a postdoc for a short time, subsequently did some, what I think will turn out to be important work in the spatial statistics of the wave field. And my guess is that if we pursue that further, we'll find that there's a very strong relationship between the statistics of those wave fields and, in fact, the statistics of braking. So Leonel did a lot of work while he was in my group. He subsequently moved to Santa Barbara, where he is now, and I look forward to your talk.
Thank you, Ken, and also want to thank the organizers. I realize I'm the youngest speaker, and happy birthday, and I'm very happy I was able to work with you. I'll take whatever. So the title of my talk is Observations of Wave-Current Interactions. Some of these measurements were actually collected while I was still a postdoc here at Scripps, and the second set of measurements that I'm going to show is work that we continue on with Ken once I move on to Santa Barbara. We had a little bit of money from BP that would allow us to continue this sort of work. Before that, I brought some pictures. So this is the C-130 that Ken was talking about that we took down to Oaxaca in Huatulco, Mexico. This is in 2004. I'm on the left, Axel Pearson right next to me, then it's Ken, Jessica, and Jim Laswell, who was at the lab at the time. It was very hard work. We spent a month. We were really suffering in a very harsh environment. This is a photo of our lab. It was a beachfront house with a private beach. Again, this is us just taking a photo within our lab. And then here's a photo of Ken working very hard in the field. He's measuring the pier in Santa Cruz, Huatulco, that was then used for georeferencing the airborne observations. Earlier, Ken mentioned National Laboratory, and I think that's how he got me into his research. One day after class, I approached him. I was really enjoying his nonlinear waves class, and he told me he was going to do an experiment in Mexico in a place with waves that it had an essentially natural laboratory where you could study waves. And I got sold immediately. I tried to sign up very, very quickly into his project, and I'm glad I did. I had a lot of fun. Okay, so back to my talk. We saw earlier Andy Jessup, he showed this, the classical curve of whitecap coverage versus wind speed. And there's lots of problems with that data. I mean, you could blame it on the methods, but also we know that the wind speed is not the whole story if you're trying to predict wave breaking. You need to know the wave field and the winds, but also the currents. This is a photo over an area with strong horizontal current shear, and is giving rise to very strong gradients in the wave breaking. You have very little breaking on the left, strong breaking in the middle, more breaking on the right. And so we designed a couple of experiments to sort of target these sort of features and actually being able to quantify the modulation of the wave field by the currents. So Jim mentioned the two ways that waves and current interact. So either the waves affect the current or vice versa, right? So current effects on waves, which I'm going to be focusing on, include refraction induced by the currents. You also have direct forcing by the currents, either it's opposing or following. An opposing current will steepen the waves. A following current will do the opposite. It will reduce the steepness of the wave. Currents can induce very large waves. For example, in South Africa, this is an area that is known for having very large waves. When you have waves coming from the Southern Ocean, encountering the Agulhas current. And also you can have very enhanced wave breaking. And the other effects, which are the effects of the waves and the currents, you can have inertial oscillations induced by the waves. You can have turbulence induced by vortex forces, enhanced kinetic energy due to wave breaking, mixing, and modulation of the surface stress. So again, in this talk, I'm going to be focusing on the first part, which is the effect of the currents on the waves. So our goal is to characterize how this wave field is modulated, including the directional spectrum, wave breaking, and wave statistics due to current effects. How did we do this? We conducted two novel airborne experiments. One during the high-res air-sea interaction experiment, which was already briefly described by others. I think Jim McWilliams talked a little bit about that experiment. It was not intended to study wave-current interactions. We were able to do a little bit of work on that. And then the second experiment in the Gulf of Mexico. So the high-res experiment, it was conducted in Northern California off Bodega Bay. This is Point Reyes. It was a multi-platform, multi-PI experiment. We had wind speeds of about 10 to 15 meters per second in typical upwelling conditions. We had winds from the northwest, and we have very strong surface currents in the area, reaching magnitudes of up to 1 meter per second. The platforms were flipped, which is shown here with a pin. Two aircrafts, the Partinaria aircraft that has been shown multiple times, including Jason earlier today, and the Scripps Twin Otter aircraft, also we have the RV Sprout collecting observations. So this is the photograph I showed earlier. I took this photo from the Partenavia aircraft. Typically for this experiment of wave current interaction, I would go in the morning in one airplane, try to look for these features, find it, go back, call Luke and Ken, and then we would coordinate the measurements with the other aircraft. So again, Flip was located over here. Winds or waves are coming from the northwest. This line of enhanced braking is shown in these two figures over here. On the left, I'm showing you the sea surface temperature as measured by the satellite. We have an upwell in front very clearly over here. On the right, we were within the footprint of a high-frequency radar array, which was that provided us supporting surface current information. So you can see that there is a very strong upwelling jet that is actually turning a little bit offshore towards the lee side or the downstream side of the headland, which is very typical of these upwelling jets. And again, this white line corresponds to this area of enhanced braking, and it happens to be right at the edge where you have very strong horizontal shear. So the instrumentation on the Twin Otter aircraft, or at least the one I'll be focusing on, includes a scanning LiDAR, the NASA Airborne Topographic Mapper, which was previously used to measure the wave field, including our work in the Gulf of Tehuantepec, a fixed LiDAR, atmospheric turbulent fluxes, and downward-looking visible imagery and infrared. Don't want it to confuse you. I'm going to introduce both experiments, and then I'm going to proceed with the results. So the second experiment in the Gulf of Mexico, we took advantage of a time when the loop current was very far north. It's hard to predict, but we took advantage that we happened to be that during this fall of 2011, the extent of the loop current was very far north, which was within reach of a small aircraft, so we could actually go measure waves interacting with this loop current. Fall are great times to do these sort of measurements because you typically have cold fronts coming from Texas, which then have very strong offshore winds flowing south, and the day after, then you have winds coming from the northeast. The results I'm going to present today are 1 day after the passage of a front, with winds not as strong. These are winds of 8 meters per second. We have waves reaching significant wave height of close to 2 meters, 1.8 meters, and surface currents exceeding 1 meter per second. This is a sea surface temperature image from reanalysis of HICOM. Since we did not have any other surface current information, just for our analysis, I'm going to be using this HICOM reanalysis data. Again, on the left, I'm showing the sea surface temperature. The dashed line shows our study area, where we actually focus on our observations. And then on the right-hand side, I'm showing you the current speed as given by HICOM near the surface. So we can see the edge of the loop current, and we actually see a little bit of an eddy activity over here. And again, the wind and the waves were coming from the northeast. So the Partenavia was equipped with the mass system that was described in the paper that Paul mentioned yesterday, always in JTech. So it had a scanning LiDAR, much better than the ATM, an infrared camera, color camera, and of course you have an inertial motion unit with GPS for georeferencing your observations. So from the two LiDARs have different modes. One is scanning, the other one is rotating, but nevertheless, if you move very fast, you sweep an area, and if you're moving much faster than the waves, you essentially measure as a frozen snapshot of the wave field. And so you essentially have eta, or the surface elevation, in 2 dimensions. And that has advantages over the typical measurements from a single point, like a buoy, like operational buoy, which do not measure directly the directional spectrum. You need to come up with, depending on the method that you use, you're going to get different answers for both the directional distribution for the spectrum. In contrast, these spatial measurements allow us to directly measure the directional details of the spectrum. So from this to the eta as a function of 2 directions, you compute it to the fast Fourier transform, and you can then obtain your directional wave number spectrum. I'm showing here on the right an example. So the most energetic waves are over here, and they're propagating to the right, as opposed to the atmospheric convention of waves from. I'm using here the oceanographic convention, waves going towards. If we integrate this spectrum in azimuth, we get the azimuth integrated spectrum, or omnidirectional spectrum. I'm showing you 2 different measurements over the same area, separated in time by only a few minutes. And so depending on the settings and the flight altitude, you're going to have different swath widths, different horizontal resolutions. So the red line is showing you flying at 200 meters above sea level, so at lower altitude, and sampling at a much faster rate, so you can actually measure finer scale waves. At a higher altitude, trying to preserve square pixels, you're limited to about 6 meter wavelengths before you get into the noise level. And just for reference, I'm putting two power laws, the typical saturation of k to the minus 3 and the so-called equilibrium after Phillips of k to the minus 2.5. So again, advantages of airborne LiDAR is that not only you measure directly the directional spectrum, but it's also the high frequencies or the smaller waves are not affected by the Doppler shift induced by the longer waves. Also, by using aircraft, we're not constrained by a given location, but we can actually go looking for interesting features, and we can actually characterize inhomogeneities of the wave field, spatial inhomogeneities of the wave field. So again, back to the high-risk experiment. So we have an upwelling front over here, an upwelling jet, have waves coming from the northwest. We're going to the southeast. And so here is the line of braking. We're going to be focusing mostly on the measurements around here. It's measured by the aircraft. So again, this is the photo I showed earlier. This is an infrared image from the aircraft, so showing you sea surface temperature, flying, trying to track this line of braking, and you see that right along this line of braking, you happen to have a very sharp sub-mesoscale front of about 0.4 degrees. So if you zoom in into this area, you see frontal instabilities of the scale of about 100 meters or so, the scale of the actual wavelength. The corresponding visible imagery from the aircraft is shown over here. So notice that you can see little braking on the left, more braking on the right. You don't really see this really enhanced line of braking due to the differences, likely because this is grazing angle versus downward looking and different dynamic range of the two cameras. So here I'm showing you the significant wave height as measured by the airplane. The gray dots show you where we have a LiDAR observation that was used to create this objective map. So we have larger waves upwind, and we have smaller waves within the area where we're very interested to see what's happening across this line of braking. And so by definition, the significant wave height is 4 times the variance, which is the area under our spectrum. So we integrate over all wave numbers, we get the variance, square root of that times 4 gives us the significant wave height. Here I'm showing spatial cross-section. So here's the warmer part of the front, the colder side of the front. It's plotted over here. So here's sea surface temperature as a function of distance. So we see a change of about 0.3 degrees at scales less than a kilometer. We can see this is the vorticity calculated from the currents. So you have a very large shear right where we have this line of breaking, so therefore it corresponds to large vorticity. The whitecaps coverage is a little small to the left and increases on the right-hand side where you have colder water. And then the winds at 30 meters as measured by the aircraft, they show actually a little decrease, a slight decrease where you find the area of enhanced breaking. So it's showing you the coupling between the waves and the atmosphere. So I'm going to introduce a few spectral moments that I'm going to use to characterize how this wave field is modulated by the currents. So again, we have the omnidirectional spectrum over here, which is just integrated in azimuth. Directional spreading, which gives you a half width, basically gives you the half width in azimuth of the directional spectrum as a function of wave number. It's given by this equation. Is plotted over here. So you get the narrowest spreading or directional spreading near the spectral peak, and it increases both toward low and higher wave numbers. If you scale your omnidirectional spectrum by k to the third, you obtain the so-called saturation spectrum, which is a measure of the slope squared and is bandwidth independent. And it is a parameter that has been used to characterize wave breaking. If you normalize the saturation by the directional spreading, you get the so-called normalized saturation, and it's shown over here. So the saturation shows a power law of k to the 1/2, whereas the normalized saturation is slightly reduced, is more flat. So let's see what happens to those parameters averaged over the spectrum across this line of breaking. So this black line shows where the line of breaking was in those three panels. The left panel shows the saturation. So we see a maximum just to the left, little saturation just to the left of the line of breaking, and then an increase on the right-hand side, consistent with what we saw in the photograph. The directional spreading shows the opposite pattern. So you see a broader spectrum just to the left of the line of breaking and a narrower spectrum on the right. When you look at the normalized saturation, you get more clear this pattern. So you have an increase over here, very large normalized saturation, very small saturation just to the left of the line of breaking, an increased saturation to the right. And again, these measurements were objectively mapped using the decorrelation length scales of the measured significant wave height. If we then look at the individual dots where we have corresponding whitecap coverage data, so here I'm showing you measurements of the whitecap coverage near this line of breaking. We have little whitecap coverage just to the left. We have more breaking over here, more breaking at the line of breaking, and also to the right. On the right, I'm showing you the saturation, the mean saturation. Looks somewhat similar to the whitecap coverage, but then when we look at the normalized saturations, it looks a lot more like the whitecap coverage. If I compute correlation coefficients between these two parameters against the whitecap coverage, I find values of R, not R squared R, of 0.64 and 0.8. suggesting that the normalized saturation gives a better characterization of the wave breaking. Now, if I compute the correlation between the whitegap coverage and the spreading, I get a negative value, so it's inversely correlated, and I get a value of 0.59, minus 0.59, that is not shown in this figure. And so what is going on? In order to try to get a handle of what is happening, I did a simple, assuming a monochromatic wave, a simple ray tracing. We have waves coming from the northwest. We have, using the dominant wavelength of 110 meters. We know that the vorticity of the currents normalized by the group velocity will give you a value of the curvature of a ray. So if a wave that doesn't encounter any current shear, it's going to go straight. The moment that you introduce current shear or vorticity, you're going to have a curvature to those rays. So that's how I generated this ray tracing exercise, showing essentially the refraction due to the currents. So what we see a convergence of the rays right around here, where we saw large saturation earlier and large wave breaking. We see spreading of the rays just to the left of the gray line, which is the line of breaking. And we see convergence of the rays on the right-hand side. So it's qualitatively consistent with the currents that we saw with the saturation. Now, moving on to the other experiment in the Gulf of Mexico, to just remind you, we're looking at waves approaching the loop current over here, and we're going to be focusing in this area over here. The black line shows you the flight track. So I'm showing here objective maps of significant wave height on the left, significant slope, so it's basically the RMS surface elevations times the peak wave number, and the whitegap coverage on the right. So we see that the wave height is modulated within 20%. So is the wave stiffness. But notice that in the areas where we have opposing waves and currents, we have very large, very steep waves. So by the way, the gray arrows show you the current direction, the black arrows show you the dominant wave direction. So we see strong changes in the directionality of the dominant wave due to this large-scale horizontal shear. So just as we did in the previous experiment, we look at the mean saturation and spreading and compare that to the whitegap coverage. So we find very large values of saturation in the northern part, also in the area of opposing waves and currents. This spreading doesn't show a clear pattern, but it shows more like an east-west asymmetry. And if I compute the correlation coefficients, again I get a positive value for the saturation, whereas I get a negative value for the directional spread. Now, in order to look at the wave statistics and how they change due to the currents, I divided my measurement area into three areas. I call them subset 1, subset 2, and subset 3. And I did that just based on the values of the significant slope. Here what I'm showing you is the statistics, the probability of exceedance of a crest exceeding a certain value normalized by the RMS surface elevation. Just for reference, the black dashed line shows you the Rayleigh distribution for linear waves. This triangles shows you the second order nonlinear theory, just accounting for the first bound, nonlinear bound harmonic, or as second order Stokes wave. So for the most well represented by the second order typhoon distribution, except for the very large waves, and particularly in this S1 area where we see very large crests exceeding second order nonlinear theory. So I did the same thing. So here I'm showing you the probability of exceedance that are individual wave height, meaning the distance from trough to crest, normalized by the significant wave height, exceeds a certain value. Just for reference, this dotted line is the so-called is the criteria normally used to define an extreme wave. So for the most part, I'm showing also the Rayleigh distribution, which corresponds to the distribution that you would expect for a linear wave, monochromatic linear wave. The moment that you have a broad-banded spectrum, you're going to have a reduction in this probability essentially because of finite bandwidth. And Forrestal in 1974 came up with the wave pool distribution, and it's shown here in gray. So for the most part, the wave pool distribution is doing a good job either bounding or representing our measurements. But again, at very large wave heights, in S1, we see large deviations approaching the Rayleigh distribution. And so part of the problem is that if you really care about extreme waves, you really need to look at the extremes rather than individual wave heights. And so this is what I'm showing here. So this is the probability of exceedance that the maximum within my record normalized by the RMS is exceeding a certain value. So the dashed lines here are showing models for linear waves. The solid line is showing you models for second order nonlinear waves. And these models are accounting for the fact that we are measuring an area, not a single point. If you're measuring at a single point, these probabilities will be much more reduced. In fact, if you consider an area and time, you would have even an increased probability of finding extreme waves. So nevertheless, we find that our measurements are well bounded by this second order nonlinear estimate, but for the most part, the linear estimate is doing a good job. So, but what we don't see is a consistent trend between these model lines and what the observations say. So for example, we don't see the solid red line being the largest, we see the green one, whereas the observations show the largest is for the S1. So it serves for engineering purposes, but it cannot explain the difference in between its different sets. Now, if we repeat this ray tracing analysis, this is the vorticity, again from this HICOM data, it's normalized by the Corellis parameter. This has a resolution of 4 kilometers. It exceeds 1, or it reaches 1. And so we have waves approaching the loop current. We have that over S1, we have a focal point. So we have convergence of the rays. Whereas we see divergence of the rays in S2, or at least parallel, and not much happening also in S3. So what this suggests is that the very large waves that we find in S1 are possibly due to enhanced nonlinearities induced by current-induced refraction. And so to conclude, we collected no observations over areas of significant wave current interactions. We find that the total wave height only varies by about 25%, 20 to 25% is not a lot. Wave breaking, in contrast, varies substantially by up to an order of magnitude or more. We find that the white coverage is well correlated with the spectral moments, positively correlated with the saturation, negatively correlated with the directional spreading. We find very large wave heights and crests over the area where you have focusing of the rays due to current-induced refraction. And these measurements are going to be very useful for benchmarking these numerical models like WAM or WaveWatch 3, and are also going to allow us to improve models of braking, including these conditions of strong wave current interactions. So for example, taking Phillips' concept and our measurements of the strength of braking to be able to predict wave braking under different conditions. So future and ongoing work. I have two funded projects at present. One is in the Gulf of Mexico to look at the coastal circulation and dispersion, and particularly looking at small scales of mesoscale fronts. This is just we just conducted the first experiment in June. We released dye patches over different water depths. We tracked them for about 6 hours total, but this is just showing you the evolution of a single dye patch of about a 100-meter radius and how it evolves very quickly. You can actually see a freshwater front over here, and within 40 minutes, the front, this dye patch is being pushed towards the front due to ageostrophic secondary circulation. It's being stretched along the front, and it's sinking very rapidly, consistent with submesoscale dynamics. The other project that I'm working on at present, I just started, is that we're going to be looking at the effect of waves on submesoscale fronts, particularly due to vortex forces, and that's going to be all done numerically within a hydrostatic framework like ROMS and WaveWatch 3 model stuff. So again, I want to thank the organizers, and I want to thank Ken for giving me the opportunity to work with you, and I congratulate you, and happy birthday, and I'm happy to work with you.
Questions?
Okay, I think you actually mentioned towards the end that this may be used as benchmark for WaveWatch, but I think the WaveWatch is completely missing this kind of small scale modulations. So if this kind of modulation is important, I think WaveWatch has no scale.
So the typical WaveWatch models, the operational ones, yeah, they don't. The work I've done in the past have always been broadbanded.
Yeah.
And it's gonna be some challenges into controlling the tail for sure. But my work, and I've done already preliminary work, I've always done broadbanded, much. I go way farther than the typical version. So we'll definitely put those kinds.
I think it's important to say that WaveWatch is really a framework rather than a single model.
Right.
There are lots of different modules that you can fit into the overall framework of WaveWatch. So it's important that in discussing WaveWatch, you have to be pretty specific about which of those modules are being used. Okay, thanks very much. Oh, sorry, Jeremy.
One more question.
Yeah.
When you do the ray tracing of the waves refracted, are you allowing them to readjust to the local wind as they go? Because the growth. I'm wondering if the growth and dissipation scale would just bend them right back to going downwind.
It's just ray tracing.
Just ray tracing.
Okay. Thank you.